Welcome back to Introduction to Higher Mathematics. In our last lecture, we discussed set theory, which of course deals with sets, collections of things like numbers, points, people, almost anything we want. We saw how to combine sets using operations like intersection, union, difference, and symmetric difference. And we saw how some of these operations are direct parallels to concepts from logic. We looked at subsets, which are made by removing elements from a set. We looked at the universal set and used it to define the complement of a set, which acts like a negation in logic. We cataloged a number of commonly used sets like the natural numbers, the integers, the rationals, the reals, and the complex. Finally, we found out why we can't have a set of sets, as it would lead to Russell's paradox. So we instead call a collection of sets a family of sets. Now it's time to take our newfound knowledge of sets and use it to extend what we can do with logic. Recall that in Lecture 3, we discussed propositional logic, in which we used letters like P, Q, and R to represent entire sentences, such as, "It will rain today," or "X is an even number." Remember, however, that second example, X is an even number, is a bit of a strange proposition, even though it's a valid one. We would need to know the value of X in order to find out whether our statement is true. Now, of course, I could create a number of separate propositions to deal with every single case. Perhaps P is 0 as an even number, Q is 1 as an even number, R is 2 as an even number, S is 3 as an even number, and so on. But that's rather tedious and repetitive, isn't it? Isn't there a better, more elegant way to accomplish what we want? By now you should know the answer in this course to that kind of question. Of course there is. Think linguistically for a moment. A proposition needs to be an entire declarative sentence. For instance, we can consider the sentence, "Brian eats sushi." A sentence contains two parts. A subject, which is either a noun or something that acts like a noun, and a predicate, which is a verb or verb phrase of some sort, whether it be a dynamic verb like eats or a more stative verb like is. So in our sentence, the subject is Brian, and the predicate is eats sushi. Simple, right? Well, it's this division of the sentence that gives insight on how to improve how we represent logic mathematically. Sets are collections of things. What are things? They're nouns. What's the subject of a sentence? A noun. So we can represent the subject of a sentence with something from a set. Now, what's left? The predicate. What we can do is store the predicate of the sentence separately from the noun, using letters like we were using for propositional variables. So instead of letting P stand for the entire sentence, X is an even number, we can let P just represent the predicate, is an even number, and rewrite our expression like this, which we can read as P of X. This gives us a great deal more flexibility. Rather than having to represent 0 as an even number and 1 as an even number with different variables, I can just write them as P of 0 and P of 1. So now that we're working with predicates, we call this new system predicate logic. Predicate logic also shows us how to handle statements like P of X. Remember that in propositional logic, the statement X is an even number is a valid proposition because it must be either true or false. But we can't evaluate such a statement on its own. In predicate logic, a predicate will evaluate as true or false depending on what its input or argument is. So P of 0 is true, and P of 1 is false. We call X a free variable because it can stand for anything. So a question we might ask is, what X could we plug into P to make P of X true? The set of all X for which P of X is true is called the truth set of P. So if P is the predicate is an even number, then the truth set of P of X is the numbers 0, 2, 4, 6, and so on, as well as the negative counterparts, -2, -4, -6, etc. We can represent the truth set of P using set builder notation as the set of all X such that P of X. When we say P of X, in this case, what we really mean mathematically is that P of X is true. Another thing that we encounter in predicate logic is a new concept called quantifiers. Suppose we have a set and some sort of predicate such as is an even number. We may want to know how many things in our set are even. Are all the numbers even? Are none of them even? Are some of them even? And are some of them not? These are some of the key words in the questions we'll answer using quantifiers. We'll continue to use is an even number as our predicate. There are two types of quantifiers that are used in predicate logic. The first is called the universal quantifier. Its symbol is an upside-down A. When we see the symbol, we read it as for all. So take a look at this expression. We would read this as for all x, p of x. So this means p of x is true for every possible x we could come up with. That's why we call it the universal quantifier, because it's universally true, or at least true for all elements in our universal set. So suppose our universal set is the integers. Think back to our lecture on proof techniques and recall one of the proofs we did. For any integer x, if x is even, then x squared is even. Look carefully. Those first two words are actually a universal quantifier. For any means basically the same thing as for all. So we can represent this symbolically like this. For all x, if p of x, then p of x squared. Now that's just fine for the universal set. But what if I want to know if a predicate is true for all members of some smaller set? For example, suppose B is the set from earlier, 2, 4, 6, 8, 10. Well then, we at least know that everything in B will be even. So we could write, for all little b, if little b is in B, then P of little b is true. Or a more common shorthand way to write it is like this. For all little b in B, P of little b is true. The second quantifier is called the existential quantifier. Its symbol is not a right side up A, as you might have been guessing, given unions and intersections, but actually it's a backwards E. You know, mathematicians seem to have this love for turning symbols upside down and backwards. I always wondered why that is. Maybe something to do with reflections and rotations. I don't know. Anyway, this symbol is instead read as there exists such that. So this expression would be read, there exists an x such that P of x. So this is different from the universal quantifier. The universal quantifier implies that P of x is true for all possible x. The existential quantifier merely says that there must be at least one x in our universal set for which P of x is true. Perhaps in reality there's two, perhaps 3 or 4. Perhaps even P is actually true for all x. Doesn't really matter. All that matters is that there exists an x for which P of x is true. We can also use the existential quantifier for a particular set, much in the same way we use the universal quantifier. Suppose that A is the set 1, 2, 3, 4, 5. Now, we can't say that P of little a is true for all little a in A, because clearly 1, 3, and 5 are odd, not even. But does there exist a little a in A that is even? Yes, in fact there are 2 and 4. But how many there are, or which ones they are, isn't the important part. The important part is that there exists some number little a, such that little a is in A, and P of little a is true. And again, we have a shorthand notation for this. We can say there exists a little a in A, such that P of little a is true. Now, look again at set B. Is it true that there exists a little b in B such that P of little b is true? Absolutely. We just said that P of little b is true for all little b in B. It would seem that the truth of a universal quantifier automatically guarantees the truth of an existential quantifier, wouldn't it? As it turns out, this is in fact true. We say that something being true for all x is a stronger statement than something being true for some x. As a review, though you may remember this from one of the homework assignments, if a stronger statement is true, it automatically implies that the weaker statement is also true. Since this is kind of like a conditional statement, we write this with a double-struck arrow, kind of like the one we use to show that two statements are logically equivalent. Of course, starting with the weaker statement, we can't necessarily determine that the stronger statement is true without extra information. There's a slight variation on the existential quantifier that occasionally comes in handy. If we put an exclamation point after the symbol, it takes on the meaning of there exists exactly one such that. This is also a stronger statement than the normal existential quantifier because it specifically says that there must be one and only one. This quantifier is commonly seen with respect to equations that have only one solution. For instance, we might see the following statement about integers. There exists exactly one integer, x, such that a times x equals a. Of course, this is true. The x this statement's talking about is, of course, 1. Quantifiers become even more useful when you combine them in various ways. For instance, let's say the universal set is the natural numbers and examine the following statement. For all x, there exists a y such that x is less than y. How can we tell if this statement's true? Let's start with the first quantifier, for all x. This means we can let x be any natural number, and this statement should be true. Now, the next quantifier, there exists a y. So once we've chosen our x, can we find a y that will make the statement, that is, x is less than y, true? Well, what it's basically saying is that given any x, we can find a y that's larger. That's absolutely true. For example, x plus 1 is larger than x. Now, look at this statement. It looks almost exactly the same as our previous statement. The only difference is that the universal and existential quantifiers and their variables have been switched. Does this mean the same thing? This statement says there exists a y such that for all x, x is less than y. So this is a little different. This implies that there should be some y for which all possible x are less than that y. This is false. First of all, the statement is basically saying that y is the greatest natural number. And since the natural numbers keep climbing to infinity, this is impossible. What's more, suppose we didn't know that the natural numbers keep going to infinity. Infinity is a strange thing that we'll be devoting some time to later. We can still provide an easy counterexample. Just let x equal y. Obviously, y can't be less than itself, which just further puts the nail in the coffin. So the moral here is to be very careful of the order in which you put your quantifiers. Putting things in a different order can change the meaning completely. In fact, something you should try on your own. Consider these other statements, also similar to the two we just looked at, and think about which ones would be true and which ones would be false. Remember that our universal set for all of these is the natural numbers. The next thing we need to look at about quantifiers is what happens when we negate them. Since quantifiers show up all the time in various definitions and theorems, it helps to know under what conditions they won't be true. First, let's look at the universal quantifier. What does it mean if it's not true that for all x, p of x is true? It would mean that there has to be something out there for which p of x is false. But wait, we know how to describe that. That sounds remarkably like an existential quantifier, doesn't it? So the opposite of for all x, p of x is true is there exists an x such that p of x is false. For instance, suppose my statement says that for all little n in the natural numbers, little n is odd. Well, we know that's not true because there exists a natural number that isn't odd, for example, 2. So we can think of negating a universal quantifier as moving the negation inside it and switching our universal quantifier to an existential quantifier. Now let's look at the existential quantifier. Perhaps its negation will follow a similar principle. If it's not true that there exists an x such that p of x is true, then that must mean that p of x is false for all x. Aha! It's just as we thought. So the opposite of there exists an x such that p of x is true is for all x, p of x is false. Perhaps we may have the statement that there exists a little n in the natural numbers such that 2n is odd. That's not true because we know that for all natural numbers n, 2n must be even. So similar to before, we can move a negation inside an existential quantifier by switching it to a universal quantifier. What's more, this method works for our compound quantifiers we were exploring earlier. Recall that the second example I gave of a compound quantifier was false. That is, it's not true that there exists a y such that for all x, x is less than y. Let's apply what we've just learned. First of all, we can move the negation into the existential and switch to a universal. So now our statement says that for all y, it is not true that for all x, x is less than y. But we can move that negation even further inside, switching the inside universal to an existential. Now our statement reads that for all y, there exists an x such that x is not less than y, that is, such that x is greater than or equal to y. Remember, that's pretty much exactly what we said when we showed the original statement was false. No matter what y you give me, I can find an x that is either equal to or greater than it. There's one more thing we can do with quantifiers. We can use them to extend our ideas of intersections and unions. Remember that both of these operations work with exactly two sets. Sure, if I wanted to have the intersection of three sets, to see what all three of them have in common, I could just find the intersection of A and B, and then find its intersection with C. Or I could find the intersection of B and C, and then find A's intersection with that result. It turns out that doing this either way will give us the same thing, as you can probably verify for yourself by trying a few examples. So we can unambiguously write A intersect B intersect C. Or if I wanted the union of 6 sets, to merge them all, I could simply write A union B, union C, union D, union E, union F for the same union. But what if perhaps I have 20 different sets, and I want to find the intersection of all of them? Do I really need to explicitly write every single set? Or is there a more compact way to write such an expression? It turns out that not only does a more succinct expression exist, but its definition will further illustrate just how the intersections and unions work. Think back to high school when you first learned about series. In fact, we briefly saw an arithmetic series in the first lecture on problem solving. 1 plus 2 plus 3 plus all the way to n equals n times n plus 1 divided by 2. But remember what we said about patterns being misleading. How do we know that we're actually dealing with an arithmetic series? Sure, we have the ellipses there, the dot, 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 but how do we know the pattern isn't actually 1, 2, 3, 0, 1, 2, 3, 0, and so on, repeating indefinitely? In these situations, it's wise to be as explicit as possible and actually specify the particular pattern we have in mind. So the way we commonly do this is to use what's called big sigma notation. We use the Greek letter sigma because it's their letter S, which in English stands for sum. To the right of the sigma, we give an expression for the rule we're using, and below and above the sigma, we give restrictions on what numbers to plug into that expression. On the bottom is the first number we plug in, and on the top is the last number. Then the sigma itself means that once we plug all the integers into that expression, starting with the first, incrementing by 1 each time, and ending with the last, we add all these expressions up to find our final sum. Notice that n is a free variable, since the summation will actually depend on the value of n. For instance, if n is 5, then the summation is 1 plus 2 plus 3 plus 4 plus 5, which equals 15. On the other hand, I is a dummy variable, because its only purpose is to specify where to plug the specified numbers into the expression. With this in mind, we can develop a similar notation for the intersection of many sets. Suppose I have a number of sets, or of course we could call it a family of sets, and I want to find the intersection of all of them. If F is our family, then we would write the intersection of all the sets in F like this: the intersection of all A's, where A is an element of F. Since F is a family, all of its elements are sets. Again, note that A is a dummy variable. It's only there to show that the sets we're intersecting come from F. But what would end up being in that intersection? Remember that for an element to be in the intersection of two sets, it must be in the first and it must be in the second. Well, if something is in the intersection of an entire family of sets, it must be in the first and the second and the third and the fourth and so on. In short, it must be in all of the sets in the family. So we can define the intersection of many sets in terms of, you guessed it, the universal quantifier. The intersection of all the sets in F is defined as the set containing all little a's, such that for all sets A and F, little a is an element of A. In other words, it contains the elements that can be found in all of the sets. The union of many sets can be written in a similar way. We just write it as the union of all A's, where A is an element of F. Now, what would be in this union? When we had two sets, for an element to be in union, it must be in either the first or in the second. So to be in the union of many sets, an element could be in the first set, or the second, or the third, or the fourth, or, in short, since of course we're talking about the inclusive or, it must be in at least one of the sets in the family. So while the intersection was defined in terms of the universal quantifier, the union is actually defined in terms of the existential quantifier. The union of all the sets in F is defined as the set containing all little a's, such that there exists a set A in F, for which little a is an element of A. In other words, it contains the elements that can be found in some set out of the ones we're looking at. On a side note, there's one more thing I didn't go over in set theory, because I figured it would fit a bit better here, now that you've seen big intersection and big union notation. So let's talk about index sets. Sometimes we want to be able to say that there's a first element in a set, a second element, a third element, and so on. Originally we said we couldn't do this, but there is a way to give a set an order when we first define it. What we can do is we can index each element of a set using what's called an index set. An index set can be thought of as a way to number each element of the set. So perhaps our index set, which we'll call I, contains the natural numbers from 1 to 100. Now, what if we wanted to make a set P containing the first 100 primes? What we could do is call the first prime number little p sub 1, which would equal 2. The next would be little p sub 2, which would be 3. Little p sub 3 would be 5, and so on. The subscripts of each element of the set is what provides our order of the primes. So we could define our set P as the set of all little p sub little I, for which little I is an element of I. We also index entire families of sets this way. Perhaps I may have a family of sets all labeled L sub little I, where I is again numbers from 1 to 100, and define each L sub little I as the set of all primes that are less than or equal to little I. So, for example, L sub 10 would be the set 2, 3, 5, 7. What's more, there's nothing saying that my index set has to be limited to just natural numbers. Suppose I have a set S of students, perhaps the students taking this class, and a family of sets all labeled C sub little s, where little s is an element of S. I could define C sub little s as the number of classes that little s has taken at the Polymath Institute. For example, C sub Michael is the set Math 150, CS 305, and CG 315. So while you can use index sets to number the elements of a set or a family, they're also much more flexible. Index sets are nice because they lend themselves particularly well to big intersection and big union notation. If I have a bunch of sets labeled A sub little I, where little I is an element of index set I, then the intersection of all those sets is easy to write. The intersection of all A sub little I, where little I is an I. And the union is done the same way. So, using our previous example, the intersection of all C sub little s would be the set of classes that all students must take, perhaps such as an orientation course or core courses. Whereas the union of all C sub little s would be the set of classes that have ever been taken by some student. The entire catalog of classes at the school. Well, that's it for predicate logic. Next time, we'll put this new kind of logic to use and go over more proof techniques. See you next time.